magnetic space. So for free space conductor, okay, just imagine for free space if I tell it is one dielectric medium. Okay, for free space, okay, free space, or else we can tell it as dielectric medium. Technically, in EMF, we will call it as dielectric medium. Um, in a dielectric medium, we not have any conductivity. So, which means that there is no conduction has been there. So, we can tell conductivity sigma is equal to 0. And also there is no charge. If I tell conductivity is 0, then what about the charge? There is no charge at all. Okay, so then I can tell the charge rho is equal to 0. So sigma is equal to is also 0 and rho is also 0. This is the condition. So mostly in your gate exam or core interview exams, they will ask free space for the wave equations. The conductivity and the charge is a valueless or the value or it is a 0. Okay, so you can mention it as 0. Okay, so further it can be derived with the big equations, but no need to do the big equation. That is just you know that how it can be derived. You can see the previous step how it can be derived del square E and del square H, and we got the full expression for electric and magnetic field. Okay, so when I'm saying that sigma and rho is equal to 0, then how this equation can be rewritten? Okay, how this equation can be rewritten for this case? Just for magnetic field, del square H minus 1 minus V square rho square H divided by dou T square equal to 0. It is a second order equation. It is a second order equation where V is nothing but wave number. Okay, where V is nothing but a wave number. Similarly, we can write it for the electric field also. Del square E minus 1 minus V square dou square E divided by dou T square equal to 0. So this is your wave equation for free space. A wave equation for free space. So by using this, we can able to define what is meant by the uniform plane wave. Uniform plane wave. So just imagine what is meant by a plane. Simply plane is what we tell one simple plane sheet. It is in 2D. Okay. So it has some length and breadth. So for this, it is uniformly distributed. That is, surface is very rough. So please imagine in your home some bed sheets. It is a one floor. You will drop it. It will be smoothened. It will be somewhat stick on with that ground. Okay. So that is called as the uniform plane wave. For uniform plane wave, some three basic properties are there. What are all the properties? Let me go with the three property. At every point in space, electric field and magnetic field are perpendicular to each other and to the direction of the travel. Okay, the first point is this. The properties. This is the your property, basic properties. At every point, PT is nothing but a point. Yes, every point is space. Electric field, I'm simply putting as E field, and magnetic field as H field are perpendicular to each other, or perpendicular to each other and to the direction and to direction of travel. You have seen the video from one point to the another point. The wave is going sinusoidally like this. So if I say this is your E field, your H field will be perpendicular to your magnetic field. It may be start with respect to here. It will be perpendicular to it. Okay, so this may produce the maybe coincide, or I am drawing like this, maybe coincide with respect to this, or it may be it have 90-degree phase shift. Okay, perpendicular means 90-degree phase shift will be there. So it has some field will be in this direction. And also please see the direction to the travel, direction of the travel. So the direction may be in the Z axis. So usually in transmission line, the direction of the thing will be in Z axis. Maybe X as E field, Y as H field. So maybe Z as the your transmission direction. Okay, so this is your first property. Let me go with the second property. The field are harmonically with the time and at the same frequency everywhere in the space. So what it means, in your free space, it is harmonically changes. Okay, harmonically changes. So then how? So the for this one best example I will give. A cricket match is going on in a stadium. Okay, so cricket match is going on in a stadium. In a home that is in a street, there are some 10 homes are there. Okay, so in first home I am there. Second home some other people will be there. Okay, so I can that is the signal will not be same at a time. Okay, some delay will be each entities. Okay, maybe the catch frequency of your system maybe varies with respect to your source station. So all station will not obtain the same instant of the signal. Okay, so this will be happens sometime. So in a one television, it will be shows like matches going on, and another TV shows like advertisement, and another TV shows like but small delay. I'm not telling a drastic delay will be there. Some small delay will be there. So that is called as harmonically changes with respect to the time. So the second point is like the second property, the fields vary harmonically with the time and at the same time and at the same frequency and at the same frequency everywhere in space. Everywhere in space. The last property says like this. The each field has the same direction, magnitude and phase at every point in any plane perpendicular to the direction of the wave travels. Okay, that is, it has the same direction, magnitude and phase at every point in any plane, but it will be perpendicular to the direction of the wave. Okay, so that point also I will write. The each field has the same direction, magnitude and phase, magnitude and phase at every point in any plane, in any plane perpendicular to the direction of wave travel. So these three properties satisfied by your uniform plane wave. But anyway, we have to apply the wave equation and we have to get the solutions of it. Suppose I am telling that it is directly going with respect to the x. Okay, I am telling that the E field, sorry, the electric field and the magnetic field. Suppose E field, I am saying E field harmonically with respect to the x direction. Okay, x direction, x direction. Similarly, H field to the x direction. In same direction, both the E field and the H field is there, but they are transverse with each other. Okay, they are transverse with each other. So if I'm says that our condition is a uniform, then the condition will be like this: dou square Ex by dou x square is equal to 0. Similarly, for magnetic field, dou square Hx divided by dou x square equal to 0. If it is a y means Ey dou y. If it is a z means z won't come. Z will be the travel of direction or direction wave, directive wave. Okay, directive wave. So the next is the characteristic impedance or the intrinsic impedance. So for that also the same wave equations we will take, but we should find what is the characteristic impedance. So now I want to ask one small question in your side. Um, that is everyone using the radio, FM radio. So how it's work? So everyone aware about the FM radio in your smart mobile phone itself. What happened? So you will use that jack. That is a headphone jack. You have to use. You have to insert it. Actually, in that terminal, you can see two-phase terminal and three-phase terminal will be there. Just insert it. That thing. If you see in your internet, you can find the impedance value. So usually the impedance should be matches with each other. Then only the signal will transmit. And one more example I will tell. So if a two per people are there, the two people from the same country, okay, same country, but one from the north and other from the south. Okay, so maybe with the help of some body language and some terms. So one person is talking purely Hindi and another person is talking purely in Tamil. Both of them not understand the language, but basically both of them from India. Okay, at least they will when they are communicating each other, at least due to the body language and some sentences, they may understand. Once they understand, they may conversate with each other. If really they not understand what happened, nothing will comes to them. Correct. In similar fashion, if the characteristic impedance is not well matched with the two antenna system, the signal will not get transmitted. Okay. So let me define what is meant by the characteristic impedance. The characteristic impedance is nothing but the characteristic impedance usually the impedance in the AC circuit or AC form, alternative circuit. In a DC, the same impedance has been termed as the how? Resistance. Okay. So the characteristic impedance is denoted by the symbol eta. It is the ratio of electric field to the magnetic field. Okay, in terms of the constant. Okay, in terms of the constant, how it can be defined. Okay, in terms of field, it is the ratio of electric field to the magnetic field. In terms of the constant of electric and magnetic field, it is given as mu divided by epsilon. Okay, mu divided by epsilon. It is the square root of permeability to the dielectric constant of the medium. Okay, so this is nothing but your characteristic impedance. Okay, so where mu is nothing but what the permeability, where epsilon is nothing but permittivity. Okay, permeability. This is permittivity. Okay, so we know that this is for the free space. Okay, so where mu is nothing but what? Mu naught into mu r, where epsilon is nothing but epsilon naught into epsilon naught. Okay, so this is for the medium, any medium. But when we consider for the free space, this can be replaced as mu naught and this can be replaced as epsilon naught. Okay, so for free space, that is our mobile signals. Okay, eta naught is equal to root of mu naught divided by epsilon naught. So what is the value of mu naught? We know that it is the constant value. It is 4 pi into 10 to the power minus 7. What is the epsilon naught value? It is 8.854 into 10 to the power minus 31. Okay. So if you simplify this thing, okay, if you simplify this step, you will get the value as 377 ohm. Okay, the 377 ohm is nothing but your constant value. Okay, constant value. In terms of pi also you can expand. It is nothing but 125. Okay, eta naught is nothing but 125. It is your characteristic impedance. Okay, so with the help of characteristic impedance, okay, so we can define the wave propagation in lossless medium. Okay, a lossless medium, then a lossy medium, and in conducting medium. So that we will detailedly study in the next class. So with this, I will wind up. If you're having any doubts or clarification, you can ask after the attendance.